Hey, this is Presh Talwalkar. Thousands of years before computers or calculators, ancient civilizations were computing square roots by hand. This Babylonian clay tablet represents one of the most important mathematical texts of the ancient Mesopotamian civilization. The Babylonians used a base 60 number system, which has enduring legacy in the 60 minutes we have in an hour. They represented numbers by cuneiform numerals. If you study the tablet closely, you may be able to make out some of the numerals that are carved in, and you can convert them into the numbers that we use in our everyday life. What did these particular numbers represent? Studying other clues in the tablet, the archaeologists were able to convert these numbers from the base 60 that the Babylonians used into the regular numbers that we use. In particular, these numbers were coefficients of a mixed number where we had a whole part and then fractions of powers of 60. So these particular numbers all represented one number that was equal to 1 plus 24 over 60 plus 51 over 60 squared plus 10 over 60 cubed. Notice that these numbers are written along the diagonal of a square. Think about a square which has a side length that's equal to 1. What's the length of the diagonal? Even the Babylonians knew this was equal to the square root of 2. So this particular number was an approximation for the square root of 2. Converting the Babylonian numbers into a modern decimal number, we end up with the approximation that square root of 2 is equal to 1.41421. These are all accurate digits of the square root of 2. So the Babylonians were correct to 5 decimal places. Their technique for computing square roots is so efficient that essentially modern computers use the same algorithm. What's even more remarkable is the technique is pretty simple to learn. In this video, I'm going to teach you how to do square roots like the Babylonians did, and it's so easy you might even be able to compute these in your head. So let's get started with an example of the square root of 17. We get started by referring to a table of squares of whole numbers. Even Babylonians started out with such tables. We want to take the square root of 17. We look for the square number that's closest to 17. This will be the number 16, which is equal to 4 squared. So imagine we were taking the square root of 16, that would be equal to 4. So the square root of 17 must be a little bit larger than 4. That'll be a starting point. So the square root of 17 is approximately equal to 4. But we know that 4 squared is equal to 16, and we want the square root of 17, which is a larger number. So we know we're going to need to add a little bit to get to the square root of 17. So we will add some fraction to make an adjustment. The numerator will be calculated as the difference between 17 and 16. 17 minus 16 is equal to 1, and that's the number in the numerator. For the denominator, we take this number 4, and all we do is we multiply it by 2. We double this number. 4 times 2 is equal to 8. So we now have our approximation. The square root of 17 is approximately equal to 4 plus 1 over 8. This works out to the decimal number 4.125. How close is this estimate? The actual value of the square root of 17 begins 4.123. So this estimate is accurate to 2 decimal places, and it's a very simple calculation. So let's do another example. What is the square root of 69? We start out with our table of squares. Which square is closest to 69? This will be 8 squared, which equals 64. So we start out that the square root of 69 is approximately equal to 8. We now need to add an adjustment. The numerator will be the difference of 69 and 64, and that is equal to 5. For the denominator, we just take this value 8 and we multiply it by 2 to get 16. So we have the square root of 69 is approximately equal to 8 plus 5 over 16, which equals 8.312. The actual value is 8.307. So again, we have a very accurate approximation. Let's do another example of the square root of 111. 111 is closest to 100, which equals 10 squared. So the square root of 111 is approximately equal to 10 plus some adjustment. The numerator will be 111 minus 100, which equals 11, and the denominator will be double 10, which is equal to 20. So the square root of 111 is approximately equal to 10 plus 11 over 20, which equals 10.55. The actual value starts out as 10.536. Again, a very accurate approximation. Now let's do a slightly different example in the square root of 23. What square number is closest to 23? This will be 25, which equals 5 squared. So the square root of 23 is approximately equal to 5. But unlike the previous examples, we know that this is too large of an estimate because 5 squared is equal to 25. Will this method still work? Let's illustrate its power. So we need to add an adjustment. The numerator in this case will be 23 minus 25, and that will be equal to negative 2. So we have a negative adjustment. Then the denominator will be equal to 5 times 2, and that will be equal to 10. So we have the square root of 23 is approximately equal to 5 plus negative 2 over 10. This works out to be 4.8. The actual value of the square root of 23 starts out as 4.796. So the technique works and is accurate even if the adjustment is a negative number. Let us now return to a final example of estimating the square root of 2 using the Babylonian method. We start out by asking which square number is closest to 2. The best we can do is 1, which is equal to 1 squared. So the square root of 2 is approximately equal to 1. We now need to add an adjustment. The numerator will be equal to 2 minus 1, which is equal to 1, and the denominator will be equal to 1 times 2, which is equal to 2. So what does this method give us? It gives us an estimate that the square root of 2 is approximately equal to 1 plus 1/2, which equals 1.5. But the actual value of the square root of 2 starts out as 1.414. So this is not a very impressive approximation. It is not accurate to 5 decimal places, as we saw in the very first clay tablet. So how did the Babylonians actually get very accurate values of the square root of 2? There is another trick in this method. We have come up with an estimate of 1.5 for the square root of 2. But there's no reason we have to stop at this point. We can take this result and repeat the whole process with this as our initial guess. So let's see how that works. So we start out that the square root of 2 is approximately equal to 1.5. What are the steps in the process now? We need to add an adjustment. The numerator will be 2 minus the square of 1.5. 1.5 squared is equal to 2.25. 2 minus 2.25 is equal to minus 0.25. So the numerator is minus 0.25. The denominator will now be double the initial estimate. So we take 1.5 multiplied by 2, which is equal to 3. Therefore, the square root of 2 is approximately equal to 1.5 plus minus 0.25 over 3. This works out to be 1.417. So we now have a more accurate approximation of the square root of 2. We are accurate to 2 decimal places. But there's no need to stop here. You can take this value as the new guess, and you could repeat the whole process. And if you do this third iteration of the process, you end up with a value of the square root of 2 that is accurate to 5 decimal places, just like the Babylonians inscribed on the clay tablet. So it is truly a remarkable method. But you might be wondering, why does it even work? How could ancient civilizations have come up with this process? Let me provide a little bit of visual intuition. To get started, I want to write down the algorithm in algebraic terms. Let's say you want to take the square root of a number s. You first find the closest square number. So let's say that s is approximately equal to a squared. Let's also write the number b to be equal to the difference of s and a squared. The Babylonian algorithm states that the square root of s is approximately equal to a plus b divided by the quantity 2a. While this formula looks weird at first, it makes a lot of sense when you consider it geometrically. Let's start out with a square that has an area that's equal to s. The side length of the square will be equal to the square root of s. In order to approximate the square root of s, let's start out with another square that has an area equal to a squared. So this might be a smaller square, so let's construct that square, and we know that its side length will be equal to a. We now have a difference between the area of the original square and the area of the square we've just constructed. So we have an L-shaped figure. The area of this L-shaped figure will be the difference of areas s minus a squared, which we will denote as b. Let's now imagine taking this area and distributing it as 2 rectangles alongside this blue square. So let's add 2 rectangles that'll have a total area of s minus a squared. But what would be the dimensions of these rectangles? Well, one side will be equal to a because that corresponds to this square we've constructed. But we don't know the other side length. Let's denote that as x. Now, what's the total area of these 2 rectangles? We have x times a plus x times a, which we want to be equal to that missing area b. This means 2xa is equal to b, so that x is equal to b divided by the quantity 2a. So let's substitute that in. Now let's look at what we have. On the one hand, we have our initial square, which has a side length that's equal to the square root of s. And now we also have another figure whose total area is equal to s, but we see that this side length is equal to a plus b divided by 2a. And therefore we have our approximation. The square root of s is approximately equal to a plus b divided by 2a. What a wonderful technique for calculating square roots, and it's truly remarkable that this algorithm has endured thousands of years. Thanks for making us one of the best communities on YouTube. See you next episode of Mind Your Decisions, where we solve the world's problems, one video at a time.